So now I want to talk about a very special kind of tree, which is a binary tree. Okay. Now a binary tree is a tree where you can say this about every node in the tree, and that is that it has at most two children. Okay. So when I'm drawing a binary tree, I might start with a root. Okay, and then I have at most two children. Okay, and now each child has at most two children. It doesn't have to have two. It could have just one, for example, right? It just has to have at most two. And likewise, eventually, we won't have any children because we're down at the bottom of the tree. So these are called binary trees. And we use them so often in computer science that they're kind of like, if you will, our favorite type of tree. Okay? So just in general, if we do have a tree that has at most n children, right, we call that an n-ary tree. So you may actually see ternary trees and quad trees and so on that are fairly common. I mean, computer graphics, we have oct trees, but mostly I think where you're going to run into are these binary trees. Now, how can we define a binary tree inductively? Okay, so this is actually a non-trivial question. Now let's see what one suggestion here. What we're going to say is that a binary tree could be the empty tree, which is nil. This is similar to what we do for lists, right? So it means that, well, I'm showing it. There's nothing, right? That is a valid binary tree. Now the other thing that it could be is a triple that has A, TL, and TR. Okay, A is whatever element we're adding, just like we did for lists, where a list was either an empty list or an element A followed by a list. In this case, we have an element A followed by two trees, or at most two trees, TL and TR, right? And the reason that I can say at most two trees is that a tree could actually be the empty tree, right? So it could just be A followed by nil, nil, but it's still, quote, two trees. Okay, so that's one definition, and it's it's pretty useful. Okay, pretty solid. Notice that I could have chosen something a little bit different. Okay, I could have said that the smallest tree was actually just A, right? And then I could have something followed by an element followed by a binary tree, possibly, right? A left tree and then a right tree. And I guess what I'm trying to say is that nil would not be a valid tree, okay? Instead, what I would say is that a node could have two subtrees, but it could also have just one, or it could have zero, okay? And that way, the smallest tree would be the tree that contains just the root, okay? Which definition is right? You're going to get a feel for that as this unit goes on. But I'm just going to say that I'm picking this method simply because it's the one that's most similar to the case for a list, okay, where we actually had an explicit empty list, okay? But in general, mathematics happens this way sometimes. There may not be a perfect way, I mean, an obviously superior way of defining a term. So we end up picking the correct definition just by looking at the properties and finding the right definition that gives us the properties that we want, okay? So we'll see how that works out. Okay, so let's try to define this tree in ACL2. Now remember def data. Def data is what lets us define data types in ACL2S, and we could define a list, for example, okay? And a list looked like the def data, and I'll just call it list, okay? And we defined it as one of nil, right? That was the empty list, or something that had put an element A in front of a list, right? And as many parentheses as we need, okay? So that was our definition for list. And notice how similar this definition of binary tree is, right? A binary tree is either nil, okay? This is our empty tree, or it is a tree that has some integer, whatever data type we want. We're building a tree of integers here, right? So this is kind of the payload, right? This is the important part. We also been calling it the element that we're adding. And then we have a left tree, right? And a right tree, right? So that's binary tree, okay? So it perfectly captures what we mean, okay? Bit of terminology that we use quite a bit. The root of the tree is just the topmost element when we draw it as a picture. When we're actually using the inductive definition, then notice that what we say is the outermost, because this tree might look like this, and put a quote and then a list, right? So what we said is that it would be a list that contains A and then the left tree and the right tree. Okay, so I'll put a big box here, and that's going to be my left. And I'll put another big box here. I hope I left enough room, and that's going to be my right. Okay, so now what is the left subtree? This is the left subtree, right? So it's going to be a list that contains A1 and then its left and its right, okay? And of course we're going to need a close parenthesis there, okay? And what does this left look like? It looks like a list, right? Which is A11, okay? That's the left tree, but actually that's not a valid tree because it needs the left subtree, which is nil, and the right subtree, which is nil, okay? And then the other one is A12, nil, nil, right? That's what the right subtree looks like. And this one will be A2, and it's going to have a left subtree and then a right subtree and then a closing parentheses. And the left subtree is a list that is A21, and then, oh, that's the end, right? So it's just nil, nil, close parentheses. And then the right subtree, right? Well, that's just nil, okay? By the way, I could have decided that was the right subtree and the other one was the left. Either way is fine. You know, I like putting it in the left first so that the nils are towards the end. Okay. So anyway, so you see that the root is actually this. This is the root, which is the outermost node of the tree. That's why outermost makes sense now. Okay. Now a leaf of the tree is a node that doesn't have any children. So let's find some. Here's A21. These children are nil nil. So this is clearly a leaf, right? A11 with a nil nil. That's another leaf. A12, nil nil, no subtree, so that's a leaf. And of course, they're easier to spot in the graph, right? It's just something that doesn't have any edges coming out of it. Okay. Now, how about internal nodes? Internal nodes are basically anything that's not a leaf. Okay. So if it has children, it's an internal node. An example of that would be A1 and A2, right? I count A as an internal node as well. Some people prefer not to, and they say that, well, that's the root. That's different. It actually makes sense to me to count it as an internal node because it makes some of the theorems easier. Okay, and so because of that, the root could be a leaf. It could also be an internal node. Okay, and it just depends on the tree. If it's just a root by itself, then clearly it's a leaf. Otherwise, it's an internal node.